I'll now request our next speaker, Professor Drew Higgins. Professor Drew Higgins is an assistant professor in chemical engineering at McMaster University. He also received a PhD in chemical engineering at the University of Waterloo, so he's one of our own and has worked in WIN for a long time. So we really look forward to Drew's talk, and welcome back, Drew.
Sushanta, thank you for that introduction. I'm really privileged to be here today, and I always enjoy seeing the familiar faces, and in this case, the names from Waterloo Institute of Nanotechnology. So big thank you to Lisa, Sushanta, Isabella, and everyone who's put this together and provided the opportunity for us to come together today and talk about nanotechnology and talk about research. So today I'm going to be talking about some catalyst material development, so electrocatalyst materials for the electrochemical conversion of carbon dioxide into fuels and into chemicals. Before I get started, as we are neighbors with an interest in nanotechnology, I just wanted to talk about some of the capabilities that we're very fortunate to have available at McMaster University, particularly in the Canadian Centre for Electron Microscopy. So we've got lots of nice instruments available. And in addition to the instruments, we've got very talented staff who like engaging with researchers, who like working with students, with postdocs, with professors, who have scientific questions that can be answered by electron microscopy capabilities. So if you're interested in getting some characterization done at the CCM, working together with the CCM, who are ultimately experts in sample preparation and characterization, please feel free to reach out to me, or feel free to reach out to the facility manager whose email is at the bottom there. His name's Brian. Very nice to work with, as well as all the staff. So I just want to highlight that because we are neighbors, and in case you didn't know that was available down the road, you know, they're at your disposal to work together on all your exciting research projects. Now, I am a millennial, so you know, I believe in evidence-based science, and you know, I'm a firm believer that climate change is real. And you know, I hope that's not too contentious of a thing to say among this room of scientists and researchers. But ultimately, if we look at what's happening in the world, we've seen global temperature increases as much as 1 degree Celsius versus pre-industrial times. And the reason this is happening, to figure out why it's happening, we need to take a look at our global energy portfolio. And at any given moment, there's about 18 terawatts of energy being consumed, where 85% of that is coming from fossil fuel sources. So fossil fuels that emit CO2 when they're consumed or when they're burned. It's expected that if we stay on this trajectory, business as usual, we're going to see global temperatures rise as much as 5 degrees Celsius over the next 80 years or so. Now you can imagine we're already seeing the consequences of global temperature increases, whether it's hurricanes, whether it's fires, whether it's floods. Now you can only imagine how bad that's going to get if we let this go off the rails and get more than 5 degrees Celsius temperature increase. Now it's predicted that if we can get ourselves on this relatively safe trajectory, and safe meaning a global temperature increase of only 2 degrees Celsius, so not perfect, but much better than 5 degrees Celsius, we can limit that. We can limit these temperature increases. And ultimately, I look at the job of us as scientists and engineers to develop new processes and develop new technologies to get us on this relatively safe trajectory. Now, this is a vision that I know I share with many researchers for what a sustainable energy future may look like. And there's a few key components of this. The first one being that our energy needs are largely met by renewable sources of energy. So things like wind, things like solar, things like hydro. And then ultimately what we want to do is we want to use molecules that are environmentally abundant to us to create the fertilizers, the fuels, and the chemicals that society depends upon. So when I say molecules that are abundantly available to us, things like nitrogen from the air, things like carbon dioxide, things like water, if we can derive our fertilizers, chemicals, and fuels from these molecules, using sustainable and renewable sources of energy to drive those conversions, that is ultimately how we can get towards sustainability as a global society. Now, at the end of the day, all of these technologies that I'm showing here rely on chemical conversions. So particularly, they rely on electrocatalyst materials to drive these energy conversions. Now, today, I'm just going to talk about one small component of this overall energy landscape, which is the electrochemical conversion of carbon dioxide into fuels and into chemicals. So just taking a step back to calibrate everybody with the definitions that I'm going to be talking and some of the terminology that I'm going to be using today, taking a step back to high school chemistry and what is a catalyst. So particularly what a catalyst is it's a material that accelerates the rate of a chemical reaction without being consumed in the process. Now there's a few properties that make up a good catalyst. So a good catalyst is something that has high activity or is able to turn over that reaction as fast as possible. A good catalyst has high selectivity. So chemical reactions can go down many different pathways, making different products as they do. We want catalysts that are selective to only one of those pathways and one of those products, or maybe two. If we have catalysts that produce a big salad of products, we're going to end up with separations challenges on our hands. We want catalysts that are stable, so they can last thousands and thousands of hours as opposed to just a couple minutes before they deactivate. And then at the end of the day, money dictates everything, so we want our catalyst materials to be low cost. Taking it one step further, an electrocatalyst is a catalyst used for an electrochemical reaction. So a reaction that involves the interconversion of chemical energy and electrical energy, or chemical reactions involving an electron transfer. So you can look at this as electricity to fuel, for example. So taking sustainably produced electricity, such as from wind and solar, and using it to drive these electrochemical conversions over a catalyst material, which is an electrocatalyst. Ultimately, these technologies rely on the development of nanostructured catalysts to enable these technologies to be techno-economically feasible. Now, this is the framework of research that we use in our lab at McMaster University. So particularly, it's a feedback loop. So all stages of this research feed back into each other. What we do when we're first trying to design a good catalyst, we read the literature, we understand what's known about that field of research, and we try to design new nanomaterials that we hypothesize are going to be good at that particular reaction. We take these nanomaterials that we synthesize, we characterize them using microscopic and spectroscopic techniques to understand what their structure is, what their properties are, and then we go and we test them for the activity, the selectivity, and the stability towards that particular reaction that we're looking at. Hopefully one day we arrive at a catalyst that's performed better than anything else that's been found before, and what we do is we integrate that into actual electrode structures or device structures. So something like a fuel cell, something like an electrolyzer. Now, as I mentioned, this research operates in a feedback loop, and there's a couple of different correlations that we use to really develop our fundamental understanding that can be fed back into the design of new materials. Particularly what we do is we correlate the results of our materials characterization, so understanding what the structure and properties are of our materials and relating that to the activity, the selectivity, and the stability that they demonstrate. What that gives us is it gives us these fundamental performance descriptors that can be looped back into our catalyst designs. Therefore, it's an iterative process, ultimately, hopefully discovering some really high performance materials that can revolutionize the performance of these electrochemical energy conversion technologies. So as I mentioned today, I'm going to be talking about electrochemical CO2 reduction. So a process that uses electricity to drive the conversion of carbon dioxide into fuels and chemicals. So different fuels that could be produced, for example, is ethylene that's used in the plastics industry, ethanol that can be used as a fuel. Today, I'm going to talk a little bit about carbon monoxide, which can be used as an intermediate for synthetic fuels production. And, I think an entry point for a technology of this nature is going to be a location where we have low-cost renewable energy available and concentrated sources of carbon dioxide that can be converted into these valuable fuels and chemicals. So there's a few different CO2 point sources that are available throughout Canada and throughout the world. I just want to highlight here that could be really nice entry points for this technology. One is if you're the average university student or faculty member that enjoys an alcoholic beverage, distilleries and breweries are point sources of CO2 because that's a byproduct of the ethanol production process. Cement manufacturing is a big CO2 source because the calcium carbonate is heated up to form calcium oxide, thereby releasing CO2 in the process. There's a lot of other fuel processing facilities and industrial plants in the petrochemical sector that are very good sources of concentrated CO2 that could be a nice entry point for a technology of this nature. So this sounds all nice, but ultimately, what's the holdup? Why are we not seeing this technology being rolled out all over the world? And ultimately, this paints a relatively simplistic picture of the problem. But at the end of the day, there are really two things that are driving the economics of this technology. The first one is the cost of electricity. Particularly, we're interested in using renewable electricity. But what we've seen is the electricity costs going down every day to the point that we're almost at 2 cents per kilowatt hour for solar energy and for wind energy in different parts of the world. So we're seeing a lot of great progress on that renewable energy cost front that is expected to continue moving into the future. And the other key thing that is really dictating the economics of these technologies, the CO2 conversion technology, is the energy conversion efficiency. So how efficient is it to convert carbon dioxide into these valuable chemicals and fuels? In this particular case, I'm showing ethylene as an example. So we want to get lower cost of electricity, renewable electricity, higher energy conversion efficiencies to drive us towards the top left of that plot where we can profitably produce ethylene by electrochemical CO2 conversion. Now, particularly, I'm going to talk a little bit about the science and the technology development. And there are a few challenges plaguing electrochemical CO2 reduction. The first is the lack of available catalysts. So you can see here a periodic table showing the different metallic elements and their selectivity under CO2 reduction conditions. The metals shown in green produce hydrogen, which is actually a side reaction that steals electrons, steals protons, thereby decreasing our energy conversion efficiency towards CO2. So any catalysts that produce hydrogen are already non-candidates because they're ultimately producing a product that for these purposes we're not interested in. Some catalysts are very good at producing carbon monoxide. A lot of times those are expensive catalysts, things like palladium, things like silver, things like gold. There are a few catalysts that are very selective for producing formic acid. One thing about formic acid is it's really great if formic acid fuel cells can become a sustainable energy technology, but right now they're not quite there. So the global market size for formic acid is just not huge that a technology of this nature would make a large impact in terms of global CO2 emissions. And then finally, you can see the lone wolf on this periodic table, which is copper, which is the only metal that's capable of producing further reduced products. So when I say further reduced, I mean products that take more than 2 electrons to make, things like hydrocarbons and things like alcohol. So you can see right off the bat, we don't have a lot of available catalysts that we can work with in our toolbox. The second thing is the activity of the catalysts that we do have. So I show here a electrochemical potential scale in terms of voltage versus RHE. And so essentially you can look at this as the chemical potential of an electron in our catalysts or in our electrode structures. As we go lower on this plot, the chemical potential of those electrons in our catalyst material get higher, thereby it's more favorable, more thermodynamically favorable for them to react with a molecule such as carbon dioxide. We're getting more reducing as we get lower electrochemical potentials. Now I show here the thermodynamic reversible potential for carbon dioxide conversion into ethylene. So thermodynamically, at any electrode potential below 0.08 volts versus the RHE scale, we can thermodynamically make ethylene from carbon dioxide. But realistically, this reaction can't occur, experimentally when we measure it, it can't occur until about 800 millivolts lower than 0.08 volts versus the RHA, which means that we're having 800 millivolts of energy loss during this process. So clearly the activity of catalyst is not where we need it to be in terms of the energy conversion efficiencies. Then the last thing I want to highlight is the selectivity of this reaction. I showed here, this is actually a simplified picture of a CO2 reduction reaction. Overall, about 15 different products can be made from CO2 electrochemically, and every single one of them has a thermodynamic reversible potential right around the range that I'm showing here for only these 4 reactions. In addition, the hydrogen evolution reaction can occur right around the same electrochemical potentials of CO2 reduction. So ultimately, when we start running a device of this nature, thermodynamically, we can make any one of these 15 different products. So selectivity becomes a really big challenge. We want to make only 1 or maybe 2 of these products so that separations are not an issue downstream. But I did mention that about 15 different products can be made from CO2 reduction. The good news is that most of these products are very widely used in industry and in the petrochemical sector. So this just shows a list of all the products that can be made from CO2 reduction. And those of you may recognize a lot of names on this list because they are widely used throughout the world. Now, taking a step back to our periodic table, one thing that I want to highlight is that most studies have looked at catalysts that are in metallic form. So this periodic table labeled by the type of products that each metal is shown is taking into account only catalysts in metallic form. So how about different forms of metal catalysts? What about catalysts that exist in ionic form, for example, or in a coordinated form? And that's going to be the topic of the research that I'm going to be talking a little bit about today. So particularly, I'm going to talk about a class of catalysts that we refer to as metal nitrogen carbon catalysts. So to the eye, it just looks like a bunch of black powder, black carbonaceous powder. But on the atomic level, it has these individual metal ion sites coordinated with nitrogen dopants, all embedded within this graphitic carbon matrix. Interestingly, the active sites that are hypothesized in these catalyst materials are these metal centers that have similar structures that are analogous to something like an iron porphyrin or a metal porphyrin structure. Now, these materials are prepared by relatively straightforward processes, simply taking a transition metal salt, a precursor for carbon and a precursor for nitrogen, blending them all together and heat treating them in a tube furnace at something like 900 degrees Celsius in nitrogen can form these types of catalysts. And I just want to talk a little bit about some of the properties of these metal nitrogen carbon catalysts and relate it back to the traditional properties of something like a homogeneous catalyst or a heterogeneous catalyst. So right off the bat, the term homogeneous catalyst means a catalyst that is in the same phase as the reacting products. So if your reacting products are in the liquid phase, that means your homogeneous catalyst is dissolved in the liquid phase. And many homogeneous catalysts have this similar structure that I show here, such as a metal ion coordinated by nitrogens within these big ligand structures. Some of the attractive properties of homogeneous catalysts is the first is that they have very well-defined active site structures. You can see that molecule that I showed there. There's going to be millions of these dispersed in a mixture acting as your catalyst, every single one of them with the same atomic structure, same electron properties. And with that being said, because they are all identical, they all have identical activities and selectivities. So you can get really good reaction selectivity. You don't have all these variations in your catalyst structure and the way they interact with reacting molecules. In principle, you can also get 100% metal utilization because every nickel site is, in principle, accessible to the reacting species within your mixture. This is not the case in something like a nanoparticle where you've got millions of metal atoms and it's only those surface metal atoms that are accessible to the reactants. Therefore, your utilization is much lower than 100%. When I'm talking about metal utilization, the big driver there is cost. If you're going to spend money putting metal into these catalysts, you might as well use all of the atoms of metal that you put in there. Interestingly, these catalysts can also be very tunable for their electronic and their absorption properties, all of which dictate the catalysis. And they can be tuned by the type of metal center that's embedded in them, or by tuning the ligand structure surrounding that metal atom. Some of the challenges of homogeneous catalysts, one is that oftentimes they require regeneration, so either reoxidation or re-reduction to whatever their active oxidation state is. So a lot of times they're running a liquid with a solid electrolyte in there that they need to absorb upon, be regenerated, and then they become active again. And another problem is that, as I mentioned, they are in the same phase as the reacting species, which means that a lot of times separating the catalyst out from the products can be a challenge when dealing with homogeneous catalysts. Heterogeneous catalysts, on the other hand, are catalysts that are in a different phase than the reacting species. So oftentimes, a heterogeneous catalyst is a solid, where the reacting phase is either a liquid or a gas. These materials have a few advantages. One is that they're electronically conductive, so they've got an infinite source of electrons available, and therefore they don't require regeneration. They don't need to be reoxidized or re-reduced in the way that homogeneous catalysts are. Because they're in a different phase from the reacting species, they don't require separations downstream as well, but they do have a few challenges. So one is that they're surface active, so there's a low utilization of the transition metal catalyst atoms that you're putting in there, just because the bulk is not accessible to the reactants, so it's not active in the process, as well as the fact that they have heterogeneous active site structures. And what that means is that every active site structure doesn't necessarily look the same. You can see in that little cartoon I put there, some of those brown atoms or some of those silver atoms are coordinated in different environments. Some are defective, some are in more ordered structures. There's just a lot of variation in how they're configured in this catalyst, and therefore there's big variations in their activities and in their selectivities. So what metal, nitrogen, carbon catalysts can do is they can actually combine the advantages of both homogeneous and heterogeneous catalysts. Because ultimately, in the end of the day, it's hypothesized that the active site structures in these materials are essentially homogeneous catalytic structures that are immobilized on a conductive carbon support. But there are some challenges related to the preparation, development, and understanding of these materials. One is controlling and characterizing the identity of the active site structures. Particularly these, as I mentioned, these materials are prepared by blending a bunch of precursors together and heat treating them at 900 degrees in nitrogen. So you can imagine at those hot temperatures, it's really hard to control what structures are formed, whereby we want to maximize the formation of the most active catalytic sites. But being able to do that, being able to direct the synthesis towards these target active sites also requires us to understand what those active sites look like and what their properties are. We also want to be able to maximize the surface concentration of active sites in these materials, as well as optimizing the pore and the transport properties of the carbon frameworks that they're in, because ultimately we need to be able to get reactants into those active site structures and get the products out. Now, this type of research, particularly for metal, nitrogen, carbon research, has been active in the fuel cell community for a while, where a class of these catalysts, particularly iron, nitrogen, carbon catalysts, is to date the best non-platinum-based fuel cell catalyst that is known. So, for example, shown here in the leftmost plot is a fuel cell polarization curve, where you can see in gray the performance of a platinum catalyst is very similar, only a little bit better than the performance of the other three materials shown there, which are different, which are iron, nitrogen, carbon catalysts prepared with different contents of naphthalene in the electrode. So the fact that we're even comparing with platinum is really important, because iron is so much cheaper than platinum. So this type of catalyst has really made an impact on the fuel cell community. Stability is still an issue, but I just want to highlight that this type of research has been going on for some time. And ultimately, As I mentioned, this research has been very active in the fuel cell community, particularly for about 20 years, where people have been making these kinds of catalysts and trying to understand them further, where some earlier investigations used time-of-flight secondary ion mass spectroscopy to first hypothesize these iron nitrogen carbon catalysts. The active sites consisted of an iron ion coordinated with 4 nitrogen species within this graphitic lattice of the nanostructured carbon material. There's been a lot of follow-up studies using different techniques like Mossbauer spectroscopy, X-ray absorption spectroscopy. And more recently, I was part of a study when I was at the Los Alamos National Lab. We were able to use STEM imaging to observe these bright spots that we hypothesized to be single atom active site structures. But a key thing that I want to mention is there's a lot of papers that do that. They do this high resolution microscopy, see bright spots, and immediately attribute that to these catalytically active metal ion centers. But any electron microscopist will tell you that contamination with things like silicon, things like iron, can really cause a lot of problems and can cause you to misinterpret those atoms as being your catalytically active structures. So what we were able to do, working with Oak Ridge National Lab, is not only image these bright spots that we attributed to being these iron centers that were active for catalysis, but we were also able to do location-specific electron energy loss spectroscopy and see that there were simultaneously present these iron atom species with nitrogen in the near vicinity that helped us further confirm our hypothesis that these catalysts consist of these iron nitrogen 4 active sites embedded within a carbon matrix. So how about the development of these metal nitrogen carbon catalysts for electrochemical CO2 reduction? Now, there's been a little bit of work done in the past few years on this topic. Particularly, I want to highlight a very nice paper that is both computational and experimental. And so you can see in red, all the data points in red are experimentally measured activities for the conversion of CO2 to carbon monoxide on these metal nitrogen carbon catalysts with a different metal center type. So there's manganese, there's iron, there's cobalt, there's nickel, and there's copper. And you can see cobalt is the most active that they tested using their preparation processes. But then they also did some computational density functional theory to predict what the activity of these different site structures would be towards the conversion of CO2 into carbon monoxide. And what they found is in some cases, this agreed with the experimental measurements they were doing, but in other cases, their computational approach predicted activities that were much higher than was actually realized experimentally. So I think at the end of the day, what this tells us is that the activity of these catalysts can be very tunable by the type of transition metal that's used in them, as well as the particular structure and coordination environment of those transition metals in these catalyst materials. So there's a lot of room for optimization and a lot of room for really understanding how these materials behave and how we can improve upon that performance. So just one example that was published 3 years ago now in this field of research, some nickel nitrogen carbon catalysts were prepared for electrochemical CO2 reduction. And the key thing that I want to highlight is that you can see on the leftmost plot here, this plot is showing the reaction selectivity of their catalyst to carbon monoxide. So the selectivity of carbon dioxide into carbon monoxide, where 100% selectivity means that every single CO2 molecule that's being converted is being converted into carbon monoxide. And you can see for these nickel nitrogen carbon catalysts, particularly the ones shown with red stars, they're achieving near 100% selectivity for the conversion of CO2 into carbon monoxide, whereby there's a TEM image of this catalyst material shown here. So it's a high surface area carbon-based material, where they hypothesize that the active site structures in this material is nickel coordinated with nitrogen within a carbon matrix. One thing that I'd also like to highlight is that this performance is very comparable to state-of-the-art silver or gold-based catalysts at only a fraction of the price. So there's clearly some promise here for this approach. But there are still two key open scientific questions that I'm going to talk about today. There's a lot more that I'm not going to highlight. Particularly, what is the exact identity or identities of the active site structures in nickel nitrogen carbon catalyst, and how can we maximize the surface concentration of those active site structures, avoiding things like nickel agglomeration or the formation of nanoparticles that are not necessarily active in the way that we want them to be. The reason we want to maximize the surface concentration of these active site structures is so that we can approach that 100% metal utilization that things like homogeneous catalysis has. So while I was still at Stanford University, I was working with a very talented PhD student named David Koshi. So a lot of work that I'm showing here today comes from him. Particularly what he did is he did a synthesis of these nickel nitrogen carbon catalysts using acrylonitrile that was polymerized, oxidatively stabilized by a heat treatment in air, followed by a pyrolysis at 900 degrees in Celsius. During the synthesis, he added a nickel salt into the mixture, and then during that 900 degrees Celsius pyrolysis, this allowed the formation of the catalytically active structures in these materials. Now we can see when we did some electron microscopy on them that these materials had a nanostructure that looked a lot like a flower, so relatively high surface area, flower-like nanostructures. And throughout this study, we varied the amount of nickel that we put in during the synthesis, and we found that the impact of the nickel did not have a significant impact on the morphology of these materials. But one thing that we did see was that at high nickel contents, and actually those labels are flipped. The bottom row of images is the high nickel contents. What we found is that at high nickel contents, we noticed the formation of nickel nanoparticles in these materials, whereby nickel was indicated to be in the low nickel materials, but not in the formation of nanoparticles. So potentially indicating that we have these atomically dispersed nickel ion active site structures embedded throughout the entire structure of these materials. So we wanted to take them and we wanted to test them for their activity towards the electrochemical carbon dioxide reaction. We had this custom designed cell that we would fill with 0.1 molar potassium bicarbonate, and then we would saturate it with CO2, constantly flowing CO2 through the electrolyte, as well as behind our electrode that had our catalyst on it, so that we had a gas diffusion electrode where CO2 was accessible to the catalyst both in the gas phase and the liquid phase. The CO2 coming out of the electrochemical cell was fed to a GC, where we were able to detect and quantify the products of the CO2 reduction reaction in the gas phase. So things like hydrogen, which is the competing reaction that we want to shut down as much as possible. Things like methane, things like carbon monoxide, and things like ethylene. Today, I'm going to particularly be focusing on carbon monoxide, but this is ultimately how we test all the different materials in our lab to see what the array of products being formed on them is. At the end of the experiments, we take out the liquid electrolyte and we do NMR spectroscopy on it. And what that allows us to do is it allows us to detect and quantify the liquid-based products that we're making through the CO2 reduction. And I'm going to talk a little bit about some performance results now, and I just want to calibrate everyone in terms of nomenclature. So I'm going to be showing a few plots where current density is indicated, a quantitative current density. And essentially, this is just a measure of the activity or the reaction rate of CO2 to CO on the activity of CO2 to carbon monoxide on our catalyst materials. And then I'll also be talking about Faradaic efficiency. So talking about the reaction selectivity towards different products. So a Faradaic efficiency of 100% means that 100% of the CO2 molecules that are reacting are going towards that particular product. So when we took these nickel nitrogen carbon nanoflower catalysts and we put them on an electrode and we tested them for the electrochemical CO2 reduction, what we found is that at electrochemical potentials between about minus 0.7 volts versus the RHE and minus 1.1 volts versus the RHE, we could get near unity selectivity towards carbon monoxide. So pretty much 100% selectivity towards carbon monoxide. And you can see on the right, in terms of the activity, the current densities towards carbon monoxide, we're getting on the order of 10 to 20 milliamps per centimeter squared of carbon monoxide before the formation of carbon monoxide saturates and the selectivity of hydrogen increases at lower electrode potentials. So this is ultimately pretty good. We want to be operating at as high of an electrode potential as possible, so as close to zero as possible. And the fact that at those potentials closer to zero, we're forming a lot of CO, we found this very, very promising, that this catalyst could be very active and very selective towards carbon monoxide. Another thing that we did is we systematically varied the amount of nickel that we put in these catalyst materials. And what we found is that when we increase the nickel content up to a certain amount, the activity for converting carbon dioxide into carbon monoxide saturated at about 3 or 4 weight % nickel. And what we think happened there is that ultimately we hit the saturation threshold of these atomically dispersed nickel sites in the carbon material. And after that, we started to see the formation of nickel and nickel oxide nanoparticles. Now, one thing that surprised us about that is that, you know, if we knew we had nickel metal or nickel oxide nanoparticles in these materials, it's well known that nickel on its own in metallic or oxide form that's going to be reduced under electrochemical conditions, it's known that that nickel can be very selective for the hydrogen evolution reaction. So we asked, why are we still seeing high selectivity for carbon monoxide even when we have these nickel nanoparticles in the materials? The reason being is when we did some high resolution TEM on these materials, that the nickel nanoparticles had a graphitic shell around it that protected them and prevented any reactants from accessing the nickel, thereby blocking them as hydrogen producing components of this catalyst and allowing us to maintain our high selectivity towards carbon monoxide. Now, we did some X-ray absorption spectroscopy of these materials, and particularly the key thing that I want to highlight is we compared the XAF spectra of our materials with that of a metallic nickel foil and a nickel phthalocyanine molecule with the structure shown at the bottom left there. And ultimately what we found is that the nickel nitrogen carbon spectra qualitatively resembled the nickel phthalocyanine with the nickel in the 2+ state. But David wasn't satisfied, and so what he ended up doing was taking his materials to Oak Ridge National Lab and being able to use high-angle annular dark field scanning transmission electron microscopy, so a mouthful there, to see these bright spots that we attributed to being nickel in these catalysts, but then actually using EELS spectroscopy to see that both nickel and nitrogen were present at these locations. So pointing once again towards the fact that nickel-nitrogen coordinated species are the active site structures in these materials. He also did some top SIMS analysis at Oak Ridge National Lab, and I'm not going to get too much into that, but the key thing to mention here is that nickel-nitrogen coordinated fragments were detected during the top SIMS measurements, very similar to what was seen for nickel phthalocyanine. So again, providing another clue that it was nitrogen coordinated nickel single sites that were the active structures in these materials. So there are still a few open scientific questions that I talked about a little bit today, but particularly what is the identity or identities of active site structures in nickel nitrogen carbon catalysts? And I've provided a little bit of insight into what that may be based on studies done in the past couple of years. But particularly, we want to know, how are these spatially distributed? A lot of these techniques that were used are bulk, so you're getting averaged information, or you're getting very localized measurements. You're only seeing a couple of the atoms in the catalyst. Can we get that spectroscopic understanding along with spatial resolution so we know where these active sites exist and we can tune these materials to perform even better? And then what is the identity and properties of these active site structures under reaction conditions? So we can characterize these materials after they're synthesized or after they're tested, but ultimately those properties may not be the same as what those properties are under reaction conditions. So we want to develop in situ and operando characterization techniques to understand these materials further. And to do that, we're working very closely with Professor Adam Hitchcock and his team at Canadian Light Source. We have a shared PhD student named Chen Yang, who's made a lot of progress early on in his PhD program to develop techniques to do soft transmission X-ray microscopy of materials that gives us both a microscopic and spectroscopic understanding of these materials with spatial resolution. So we've taken some of these nickel catalysts. You can see it here. I'm not going to dive into it too much, but ultimately we get a microscopic image of this catalyst material with every region in this material being correlated with an X-ray absorption spectroscopy spectra that can give us understanding of what species exist in this catalyst and where. We're also taking it one step further using some electrochemical cells developed at the University of Beirut by Martin Ops, Pablo Ignio and his team. And so it's taking these materials, depositing them onto working electrodes, flowing electrolytes and our reactants in, and doing STXM of these materials under reaction conditions. Just some preliminary results on that front. What we did first is we took our working electrode and we electrochemically deposited copper, which is a very good electrochemical CO2 reduction catalyst, in a copper sulfate solution. Then we switched out the electrolyte to put in sodium bicarbonate that was purged with CO2, so our reactant purged electrolyte. And we did characterization of the copper electrode at varying electrochemical potentials. So we got a very nice cyclic voltammetry profile, and we're able to collect STXM images at different electrochemical potentials, setting the stage for doing some in situ characterization of catalyst materials under electrochemical CO2 reduction conditions. So with that, I just want to kind of wrap this up and just show this feedback loop that hopefully I provided a small snapshot of how we operate within this feedback loop in our group. I also show some of the different research areas that my group is involved in. And I'd like to acknowledge all the people that have contributed, both at McMaster, Stanford, and Los Alamos, to the results that I showed today. I also show our group photo on the left. I think that's more realistic of what group meetings look like these days. And actually, this was a combined meeting with Professor Adam Hitchcock and his team. I'd also like to thank all the funding agencies. And most of all, I'd like to thank all of you. I'd like to thank the Waterloo Institute of Nanotechnology for this incredible recognition. And I did have a really great time as part of the Waterloo Institute of Nanotechnology from 2009 to 2015. And I'll always consider myself part of the WIN family. So I hope you all feel the same. And thank you all very much for your attendance.